Hi, welcome back. In this set of lectures, we're talking about randomness and random walks. What I want to do in this very short lecture is just unpack a little bit of what we mean by randomness, because randomness means different things to different people, and oftentimes when you see randomness in a model, it has different conceptual underpinnings. It means different things to different people. So let's talk a little bit about what's meant by the concept of randomness. Now, to get us started, we've got to start up again by talking about a probability distribution. So remember we talked about a probability distribution saying, here's our set of possible outcomes along here, and here's the probability that they occur. And if they're all equally likely, like they just were in the example we saw of the path-dependent process, then you're going to get a distribution that looks like this. But more commonly, we see distributions that are normally distributed, and we get this nice bell curve, right? Remember the bell curve when we talked about the central limit theorem. So when we talk about randomness, we're going to care about what the distribution of that randomness is, and also where it comes from. And that randomness can have lots of shapes, right? It can be uniform, it can be a bell curve, and it can even be a long tail, as we saw in that distribution on network graphs. So lots of different distributions out there, lots of different forms of randomness. Now, when we write randomness in models, what we often use is the following conceit. We say that instead of just having some value x, there's also a little error term, an epsilon. So there's an x term, which is the value we're concerned with, and then there's some randomness or error that gets in the way. And we want to talk about where that error can come from, where the randomness comes from in models, and why so many models, whether you look in economics, physics, sociology, biology, engineering, you're always going to see these epsilon terms. They're everywhere. Where do they come from? What's the reason for it? Well, one reason is just noise or measurement error. So if you think about measuring the luminosity of a star, let's say, you look through this telescope and you get some measurement. Well, there's different levels of ambient light, there's different humidity, there's maybe a little bit of dust on the glass. All those things are going to contribute to creating small deviations in actually getting the true measurement. So instead of getting, if the true luminosity is L, you might get L plus epsilon or L minus epsilon. You're going to be off by a tiny bit. So noise is one reason, just variation up there in the environment. Second is error. So suppose you run an ice cream store and you want people to dip ice cream scoops so that they weigh exactly 4 ounces. So each ice cream cone has exactly 4 ounces of ice cream on it. Well, different people are going to be dipping, the ice cream's hard and soft, people are going to make mistakes. So instead of selling exactly 4 ounces of ice cream in each cone, some people are going to get big cones, some people are going to get small cones, and that's just how it's going to be because people make mistakes. So error is another reason you see epsilon. Remember we talked about 6 sigma early on. Well, 6 sigma is all about reducing the size of that error. But even if you don't reduce as much as you can, there's still going to be some, and that's another cause of randomness. Third cause of randomness is uncertainty. So suppose you undertake a huge project, like building Big Ben, for instance. Well, what you have is you have an estimate of how much it's going to cost to build that project. But that's just an estimate. What's actually going to play out in reality is going to be different because some materials may cost more than you expected, some may cost less. There may be problems along the way as the project unfolds. And so as a result, instead of the cost being what you expected to be, there's going to be some uncertainty because the world may change as you're moving along in the process. So therefore, uncertainty is another reason why we see randomness in models. Fourth reason is complexity. Now, remember we talked in our models how systems can go to equilibrium, they can be periodic, they can be random, or they can be complex. The thing is, remember when we talked about these processes in which there's lots of little interacting things, well, those can produce all sorts of interesting patterns that are complex that we really can't predict, we can't know. So if the world is really complex, we may not know what's going to happen, so we say, okay, well, X is our best bet, but because I don't really know what's happening, I'm going to throw in an error term just because that'll correct for maybe what I get wrong. So I know I'm not going to be exactly right, so there's going to be some error. So complexity and uncertainty can actually get modeled in the same way as just a plus epsilon term. Now, there's going to be problems with doing that. We'll see some of those a little bit later in the course. But for the moment, it's not a bad idea to think about just if you're not sure what's going to happen, whether you're uncertain or whether the process is complex, by throwing in some sort of error term. And finally, epsilon can be in there, that error term, that randomness can occur just through capriciousness. People are hard to predict. So if I'm running a model of people, I don't want to say, I know what those people are going to do. Instead, I might say, well, they're probably going to do this, but who knows, right? They're people. They're crazy. They might do anything. And so we put in a little bit of an error term. So all sorts of reasons why things may not go as we expect. There can be noise, there can be error, there can be capriciousness, there can be uncertainty, there can be complexity of the underlying process. So when we think about these models, these random models that we're going to study, There's all sorts of things that can come into play to make the outcome not be what we expect, but to include a little error term. And that error is going to introduce things like luck that make it really interesting when you think about why is someone successful and why is someone not successful. All right, thank you.